Okay then, so we've talked about lots of logical operations and different things that we can do in these kind of categories set to the power of c. Now, one thing that we haven't mentioned is about some kind of colimits. And so one particular colimit we didn't mention was the idea of a co-equalizer. Now, I'm not actually going to mention that in this video, because if you have a look in the video Elementary Machinery, you'll find I describe co-equalizers and also give a sort of rough outline about how we can cook up any kind of co-limit in set to the power of c in that video. And there are various sort of added links to the description of that video where you can find out how to solve this problem in generality. Anyway, that's one kind of loose end I wanted to tie up. Another one is these kind of other logical operations which I haven't discussed yet. So there's two of them really which are standing out, and those are the ideas of for all and that exist. So let me start with for all. Basically, I'm going to just quickly recap some of the kind of theory of this kind of universal quantifier, and then recap a theorem which we can use in set to the power of c to really calculate the kind of objects associated with things like this. So consider a relation r on b times a in set to the power of c. So what we're really interested in is this thing which is sometimes called for all little a r. And this is really just shorthand for this. The subobject classified by for all subscript capital A after the transpose of chi of r. And so here for all subscript capital A is the classifying arrow of the name of t after exclamation mark a. And so you can see if we pull back true along for all capital A, we get the name of t after exclamation mark a. And then if we pull this back along the transpose of chi of r, we get this thing for all little ar that we're interested in. Why are we interested in this? Well, it crops up quite a lot in the Mitchell-Benebow language. Now, I'm not really supposed to be focusing on the Mitchell-Benebow language in this video, so this is just going to be a very short kind of toe dipped into the language, but suffice to say, if we have this kind of extension here, for all little a of type capital A phi extended over b, we could think of this as the subobject classified by the interpretation of for all a phi over b, which, expanding it out, is the subobject classified by the interpretation of for all subscript a lambda a phi interpreted over b, and we want the subobject classified by that. Well, this is the subobject classified by for all subscript a interpretation of phi over b and a transposed, and we want the subobject classified by that. And if we want to write r is equal to the subobject classified by the interpretation of phi over b and a, or equivalently chi of r is the interpretation of phi over b and a, well, if we write that, then we can rewrite this as for all subscript a transpose of chi of r and the subobject classified by that, which is what we've been calling for all little a r. So you see that this thing crops up. Basically, we can pick an appropriate, we can find an appropriate relation r so that we can write that these two things are equal. Okay, so the reason this is relevant then is because this is something that crops up quite a lot in the Mitchell-Benebow language, and we can sort of write it in terms of this for all little a r kind of expression. And then the fact of the matter is that we have a result which allows us to understand this kind of subobject for all little a r quite well. So if you can see by this diagram that for all little a r is a subobject of b here, and we can actually characterize the arrows which are in it quite easily. So this theorem 13.9, which we've referred to quite a lot in the last few videos, can do this job for us. So what it says is that if we have an arrow W from H into B, then we're going to have that W is in for all AR if and only if W times the identity arrow of A is in R. So how can we use this result? Well, if we really wanted to understand this kind of thing in a category like set to the power of C, we can of course understand it as an inclusion monic, right? And so in that case, what we'd be interested in is for sort of arrows that are coming from Hom functors, when are they going to be in this kind of subobject? And so we can use just a special case of theorem 13.9, and basically we can write something like this. In set to the power of C, when we pick an object E of our category C, and we have a relation little r, a subobject of B times A, then we have that if we want to consider this for all AR thing as an inclusion monic into B, then the E figures of that subobject, in that case, the ETH component of for all little a, little r is just an inclusion function, but then for all a capital R of E is basically the set of E figures of B that are included in the subobject, and we can think of that as the set of theta in B of E, such that theta under arrow is in for all little a, little r, or equivalently, according to this kind of result, we can then write that as the set of all theta in B of E, such that theta under arrow times the identity of A is in little r. And that's nice because this is really the kind of thing that we can get a handle on. So we can sort of manually check whether these different sorts of arrows corresponding to E-type elements are actually going to be in this kind of subobject here, are actually going to be in this. So this is nice because we can manually kind of check if this kind of arrow, theta under arrow times identity of A, is going to be in R for these different theta in B of E here. And therefore we can really kind of compute the nature of this kind of subset. And this really allows us to get a handle on the nature of this kind of subobject in set to the power of C, which, as we see here, does really occur in this Mitchell-Benebow language quite a lot. And so given this, then there's only really one thing missing, which is this kind of understanding of the existential quantifiers. Now, as I've said before, reading McClarty, which is the main sort of topos theory book I've been reading recently, it doesn't shed an enormous amount of light on the nature of this existential quantifier. but I have found results from other books which I'm sort of hoping are equivalent. So take what I'm about to say with a big sort of pinch of salt, but essentially the theory seems to work like this. Suppose we are interested, let's say, in the Mitchell-Benabal language in this kind of expression. Again, I'm going to dip a toe into the Mitchell-Benabal language. It's not really totally essential to understand what I'm saying here, but it's one of the main places that motivates wanting to understand the existential quantifier. So it seems like a good kind of digression to make at the moment. So let's say we're interested in understanding this kind of extension here, the extension of there exists a phi over b. Well, there's a question of what that means, and there's a sort of long-winded explanation of this in McClarty where he gives a formula for there exists in terms of foralls, and it's quite complicated. Now, I think there is actually a simpler, in fact, a couple of simpler ways to view this, which are quite fitting with the kind of tools that we've been developing, which are the kind of tools that we can understand properly in this category set to the power of c. So one of these is that, let's say we just have that phi here just has these three variables, little b and little a. Well, then, I think that one possible route, as suggested by Goldblatt, is if we take this kind of extension here, I think we can write it as there exists subscript A after the transpose of the interpretation of phi over B and A, and then get the subobject classified by that. I think that these two things are equal. Now, I'll explain what this there exists subscript A thing is in a moment. But just to say yet another way I think we can understand this. I mean, of course, another way we can rewrite this is there exists subscript A chi of R transpose, and then the subobject classified by that. Now, that's nice because it looks very, very similar to the kind of stuff we were just looking at with forall. And here, of course, we'd want that chi of R is equal to the interpretation of phi over B and A, or equivalently that R is equal to the subobject classified by the interpretation of phi over B and A. Anyway, I'll explain what this exists subscript A thing is momentarily, because it is the kind of thing that I think we can handle. But I think there's also perhaps another way we can write this, when we have this sort of way of substituting R in here. And like I say, take this with a pinch of salt because it needs checking and thinking about. But I think we can also write it as exists little a R, or, this is actually just kind of meaningless notation for us at the moment, but this is much more concrete. I think we can also write it like this, as the image of P1 after R. So here's the idea. Basically, we have this sort of arrow phi here, which is an arrow from B times A to omega. So we can think of this as the classifying arrow of some subobject R of B times A. And then, let's just, for an example, to get some intuition, let's think about what this means in the category of sets. For example, it's basically like a subset of the product of B and A. And then if we do a projection P1 after that, and we take the image, we'll essentially be selecting these elements of B that have something sent to them. In other words, these kind of things which are such that there exists an A, such that there's something in relation to this kind of B. So this seems to make a fair amount of sense. Anyway, I said I'd explain what this exists subscript A. Oh, and by the way, this is nice because this is the kind of thing that we can really understand, because we know how the kind of image of arrows works, what it looks like in set to the power of C. And so we can always write this kind of thing and make a fair amount of sense out of this kind of way of thinking of existential quantifiers. But what about this other way? There exists subscript A. What's that? Well, if we have this kind of object here, omega to the power of y times y, well, there's going to be this evaluation arrow, which is an arrow from this to omega. And we can think of that evaluation arrow as the classifying arrow of a subobject of omega to the power of y times y. And that subobject is what we call in subscript y. So this in subscript y, or if you like epsilon subscript y, this is the subobject of omega to the power of y times y classified by the evaluation arrow associated with this exponential object. So that's what this is. Now, bearing this in mind, if we do P2 after this thing, this gives us an arrow from this top left corner to omega to the power of y. And then suppose we do an epimono factorization of that. So we sort of decompose this kind of arrow like this into being this kind of epic Q followed by this monomorphism, which is indeed just the image of P2 after n to the power of y. So it's the image of these two arrows. And so that red arrow there, image of P2 after n to the power of y, that's going to be a subobject of omega to the power of y. And so the definition of exists subscript y is going to be as the classifying arrow of this red arrow. Well, okay, that's that. Except I was using an A up above, so let me just adapt the notation. So if we change these Y's into A's, Yeah, there we go. Then it's more matching with what we've got up there. Okay, so of course this is just the same kind of thing I just said, just with the y's replaced with a's. But anyway, we basically see that this thing here is defined as the classifying arrow of this sub-object here of omega to the power of a, and this is just in a, and this is just p2 after in a, where in a is the sub-object classified by the evaluation arrow associated with omega to the power of a times a.